Hello everyone. Today we will start with the signaling system unit 1 and the concept of this is introduction to signaling system. This is a table of contents. First one is the major application areas. Continuous time signal, CT signal this is known as. Then we have the discrete time signals, elementary signal detail, classification of continuous time signals and discrete time signals, and then description of continuous time and discrete time systems. Starting with the major application area, I will say, firstly we need to know what we mean by the communication, why we are using the signal link systems. Basically we need to see these are the major application areas for using signal link systems. First one is the communication, audio and speech processing, image video processing, acoustic signals, circuit designing, biomedical engineering, bioinformatics, energy generation and distribution system, chemical process control, then we have aeronautics. All these not only limited to these application areas, we have so many areas nowadays where signal system is being used as a major concern. Without the knowledge of the signaling system, it is not possible basically to go through these particular application areas. So starting with the signals and system. If I consider starting with this, we need to know that what we mean by the signals. Signal is basically a physical phenomena which conveys information. Any useful information if you are getting, that is basically considered as a signal. Not all the signals are considered like signal, they can be the random signals, but all the information signals can be considered as basically a signal which conveys the information. So function, it can also be considered as a function of one or more independent variables. Like we can say this is a function, it is depending upon the independent variables say x, y and z, which contains some information that needs to be circulated. If I discuss about the system, it is basically a physical media which does processing on the signal. Basically, we have the signal on the input side. We can see, you can just clarify it from here. Suppose this is a system which is considered as a physical media. Input signal is being given to the system and we get the output. Here one point is to be noted that the input signals are basically known as the excitation signals and output signal is also known as the response signals. So basically the signals are the signals which contain the information. Whenever these are given to a system which is basically a physical media for the processing, then we get output signal in the response. So this slide basically contains the knowledge about the signals and the systems. Here the same thing we have detailed in here. Excitation signals are applied to the input and in response we get the output signal. One more important thing we need to cover in this, that these systems can do any type of processing like multiplication, amplification, subtraction, addition, convolution. Any type of applications cover under this purpose. So coming to a communication system as a system. This is basically a diagram for a general basic communication system. Here we can say, here we have a transmitter, channel, receiver. In the output side we have the noisy information signal and at the input side we have the information signal. A very important thing we need to know it here. Transmitter is basically a device that used to send the information signal to the receiver. That's a very important thing. Main noise comes from the channel. Main noise comes from the channel. Obviously the transmitter and the receiver section also include a part of noise, but mainly the noise comes from the channel. We can say that not all the systems are ideal. Obviously, whenever we send any information signal, in the output we get some noisy information signal and that noise is basically included mainly from the channel. So this is a communication system. It includes basically the information signal plus noise signals. So whenever we consider with the communication system designing, we always keep the noise signals that are being also added from the channel, from the transmitter, from the receiver. Right? So coming to the next slide, we have the types of the signal. It's a very basic thing, like what are the basic types of signal? Up to this point, we have studied the signals, that is the information, and the system, that is a physical device. Then the communication system. Communication system is basically a system which passes the input signal through a channel and gives it output. Now we will discuss about the types of the signal. If I discuss the basic type of signals are continuous time signal and discrete time signals. So continuous time signal can be any signal which is a function of the time, and discrete time signal denoted by xn is any signal which is a function of n, and n is an integer here. Continuous time signal and discrete time signals are basically the major classifications of the signal, and discrete time signals are obtained after the sampling of continuous time signal. If we sample continuous time signal, so basically we get x n t. If t is 1, then we get x n. This is equivalent to xn. So whenever we sample input signal or continuous time signal, we get the discrete time signals. So after this, we have the elementary signals. In elementary signals, we have number of elementary signals. First one is the unit impulse signal. Then is unit step signal, then we have the signum signal, then we have the ramp signal, then we have the sinusoidal signal. So we will be doing these signals in detail in the next slides one by one. Coming to the unit impulse signal. Unit impulse signal is denoted by delta n. It's a very important thing that unit impulse signal is the first major elementary signal which is denoted by delta n. And its value is 1 at n is equal to 0 and 0 at n not equal to 0. That means delta n value is 1 at n is equal to 0, its value is 1. At all other points, its value is 0. So this is denoted by delta n, and this is also known as a delta function. Impulse function, unit impulse signal, and delta function. Right? So, if I ask about the scaling property and the sampling property, I can say a summation of amplitude a delta n minus n naught xn is equal to a xn naught, because its value is defined only at n is equal to 0. Coming to the next elementary signal, you have the unit step function or unit step signal. It is denoted by u of n. Unit step function is denoted by u of n, and its value is 1 for n greater than equal to 0. It's very important signal. Whenever we do the elementary signal, these signals are basically used for designing of the systems. So it is also considered as a very important signal in signaling systems. Unit step function denoted by u of n, and its value is 1 for all the values of n greater than equal to 0. Right? At negative values, at n negative or n less than 0, its value is 0. Right? So we can draw it like this. This is a graphical representation of unit step. Right? And this is the expression based how we denote the unit step. This is expression based denotions, and this is a graphical representation and mathematical representation of unit step signals. So coming to the next type of elementary signal, we have the signum function. Signal function is denoted by SGN n. It's also a third type of elementary signal. It's a very important signal in the signal and systems. Its value is 1 for n greater than 0. You can see from the graphical representation, for all the values greater than 0, its value is 1. At n is equal to 0, its value is 0. And for n less than 0, its value is -1. So we have the both mathematical representation as well as the graphical representation for the signum function. Then we have the fourth type of elementary signal, that is a unit ramp signal. We can see, just get to see first the graphical representation of this signal. This signal is denoted by ramp n. How we denote it? This is ramp n, and in some books we also denote it by r of n. A very important signal. We can see the graphical representation. At n is equal to 0, its value is 0. At n is equal to 1, it's 1. At n is equal to 2. At n is equal to 2, its value is 2. At n3, its value is 3. At n4, its value is 4. You can see at n8, its value is 8. So I can say at its general form will be n for n greater than equal to 0. When we have the graphical representation, we can see it from here. Its value is n for n greater than equal to 0, and for all other values n less than 0, this side its value is 0. So it is also considered as an important discrete type function, elementary signal, that is a unit ramp function. So coming to the next, we have the sinusoidal sequence. This is the most important form of it, the sinusoidal wave, the cosine waves. All the waveforms come under this elementary signal. So whatever we use in the signaling system, sinusoidal signals are playing an important role, because maximum we have the audio signals and any other signal, they are the sinusoidal in nature, right? If I say its value is given by xn is equal to a cos n omega naught plus phi. Here phi is the phase angle and n is the integer that is used for the sinusoidal signals. So sinusoidal signals can be cosine wave as well as a sine wave. Right? We can see the graphical representation of the discrete signal. This is in form of sinusoidal wave but discrete in nature. After this elementary signal, we have the classifications of signals. In the classification of signals, we have first periodic and non-periodic. Then we have deterministic, random signals, even and odd signals, energy and the power signal. So covering all these topics one by one, we will be starting with first signal, that is periodic signal. So coming to the periodic signal, it's a very important signal. Any function is periodic if the signal is repeating after a regular interval of time. So I repeat, any signal is periodic signal which repeats after regular interval of time, and if it does not repeat, that is termed as a non-periodic signal. So the general form of the periodic signal is this one. If I consider that GT is any signal, if it is repeating after GT plus NT, so this NT is the fundamental period, T is the fundamental period after which the signal repeats. So I can draw it here also. Suppose this is the signal. Let it be the continuous time signal if I will take the case. This signal, let it be the time period is T, T1. After this particular instance, let the signal is repeating. So after T1 up to this point, this signal is the same. After this T1 time, the signal is repeating itself. So this type of signal is considered to be a periodic signal. Any signal which is repeating after a particular instant of time, that is considered as a periodic signal, and the time period for which it is after which it is repeating, this time period is known as fundamental time period. So the general equation in the case of discrete is, this is for the continuous. For the discrete, xn is equal to xn plus n. For discrete, the duration after which the signal is repeating, this is capital N. So we have described it for both the cases, continuous as well as discrete. In the continuous, we have a T as a fundamental period, and in discrete, we have as N as a period. Those signals which do not repeat, which are not periodic, obviously are known as aperiodic signals. Something like this. The signal is not repeating. Any signal which is not repeating after a certain instant of time, this is known as aperiodic or non-periodic signals. So after periodic signals and non-periodic, we have deterministic and non-deterministic signals. If I ask about the dictionary meaning of the deterministic signal, any signals whose value can be calculated, they are termed as a deterministic signals. And any signals whose value cannot be calculated are known as non-deterministic signal. Any signal is deterministic if there is no uncertainty with respect to the time. Any signal whose value cannot be calculated, they are known as non-deterministic. In other terms, I can say any signal whose formula is there, that is deterministic. जिसका भी formula है, that is deterministic. And any signal which cannot be shown using a general formula or mathematical formula, they are termed as non-deterministic. So mathematical formula, you can say any which is described using a mathematical formula, for which we can describe a formula, general formula, that those are known as deterministic signals. One important thing also here, that non-deterministic signals are also known as a random signals. Non-deterministics are also known as a random. So then sometimes they ask for the deterministic and the random signals. So this is a basically description. This is a sine wave. Its mathematical formula can be described. So it's a type of deterministic signal. And any random signal whose value is random, which formula cannot be described by a mathematical equation, these are known as a random signal or non-deterministic signals. Right? So coming for the next one, this was the periodic, non-periodic, deterministic, non-deterministic. So coming for the next one, we have even and odd signals. Even signal, we know that what we mean by the even signal, right? Even signals are symmetric in nature. Even signals are symmetric in nature. They are symmetric about axis, you can say. We can see this diagram. This signal is basically an even signal. This is an example of an even signal because there is symmetry in the left side and the right side both. There is a symmetry in the left side and right side both. We can see this diagram. Basically, it is symmetrical about origin. So any signal which is symmetric about the origin or the vertical axis, that those are known as even signals. And other signals which are non-symmetric about the origin, these are known as basically the odd signals. And the important equation about the even and the odd signal is, in the case of even signal, we have x of minus t is equal to x of t. But in the odd signal, we have x of minus t is equal to minus of xt. So basically, negative signals and the positive signals value is same in the case of even signal. But here we have the negative amplitude in the case of vertical axis. So the property, the condition for the even and odd signal is, for the even signal, x of minus t, that is a negative value, this value is also equal to the x of t, but not in the case of odd signal, it is a negative amplitude. We can say here we have the negative amplitude. Right? Right. So the fourth type of signals, they are energy and the power signals. Energy of any signal, any sequence is defined by this formula and denoted by capital E. This is summation of n minus infinity to infinity x whole square. That means we know that any signal whose energy is basically finite, they are known as energy signals. And any signal whose power is finite, they are known as a power signal. So we have the formulas for the energy, finding out the energy of the signal and the power of the signal. Energy of the signal is given by the first, this formula, and the power of signal is given by the second of the formula. And if energy is finite over the time, this is known as an energy signal. And if the power is finite, obviously this is known as a power signal. After the signals, elementary signals, the type of the signals, we have very important aspect, that is the systems. Systems are the set of elementary or the functional blocks which are connected together and produce an output. I told you earlier also that the systems are basically the physical devices. It can be number of the devices connected together to give a response. Basically, the input signal is known as the excitation signal or the input signal. Whenever we apply to the systems having a response agent, that is an impulse response agent, they produce an output which is also known as a response. Right? So systems are any physical devices. It can be number of the devices connected together to give a particular output. These systems can be an amplifier for the convolution. It can be a mouse device. It can be any device which perform operation on the input signals. So after the system definition, we have the classifications of the system. First, we have the dynamic and the static systems. Then we have time variant, time invariant system, linear and non-linear system, causal, non-causal systems, and stable and unstable systems. So we will be doing the classification of systems one by one. Starting with, this is basically how we denote the system. So this is XA. Here we have the Y. We can say T here. T means system is performing operation on the signal XA. Y is equal to T. This is used as a transform. That means to say, if we are using a system and the input signal, that means this system is doing an operation on input signal. For this purpose, we use a capital T. Right? So this is a simple, basically mathematical modeling of transformation, and this is used in operator. T operator is basically used as a transformation of input signal to get an output signal. Right? So starting with the first type of system, we have the dynamic and the static system. So dynamic static system is a memoryless system. It is a memoryless system, and dynamic system is a memory system. Any system, if we can see the example 1, yt is equal to 2 of xt. We can see it from here. Output in example number 1 is depending upon only the present input. Output in example 1 is depending upon only present input. Example number 1. xt is a present input, yt is a present output. Right? So it is depending only on the present input, output is depending only on the present input. So basically these type of systems are known as a static systems. And dynamic system, this is not dependent only on the present input but also on the past input. So this type is basically the present input and this is a past input. So any type of systems, we can take the two examples for the static and dynamic. So any type of systems whose output depends upon present as well as the past inputs. So these types are known as the dynamic systems. So coming for the next type of systems, we have the linear and non-linear. A very important aspect of the linear system is any system is said to be linear if it follows superposition principle. If it follows superposition principle and homogeneity principle, like if we are applying input or we are changing input, output gets also changed. So basically linearity should be there in the system. So any system is said to be linear if it is satisfying the superposition principle and homogeneity principle. So here we are considering an operator and a system operator, transforming operator T, this one, and input is applied to the system. When we get the output yn is equal to T of xn, we can see that a x1n, b x2n, it is a, that means our operator is applied, x1n plus b x2n, that is operator is applied on this. In case of linearity point, the left hand side of superposition principle if we apply, it should be equal to the right hand side. So that means we can say the left hand side equation for the superposition principle should equate accordingly. So according to the superposition and homogeneity principle, we get the equation as written here, right? And we have to see that the system operator, that the transforming operator is applied on this particular system. So coming for the next system, we have time variant and time invariant system. It's also a very important type of system. variant if its output and input characteristics vary with time, right? Otherwise, system is said to be time invariant. If both are varying, both characteristics are varying with time, this is said to be time variant. Otherwise, if they are not varying with time, then they are known as time invariant. The condition for time variant, you can say yn comma t is equal to yn minus t. And condition for time variant is yn comma t is not equal to n minus t. This we can see detailed in the next lecture related to the example related to time invariant, so that we can have more detail about the time variant and invariant systems. Then we have the causal and the non-causal systems. Causal system is said to be causal if output is depending upon the present and the past input, but not on the future. That is the main aspects here. We can see it here. System is said to be causal if output depends upon present and the past input, but does not depend upon the future input. That means we can see from the example number 1, output is yn and it is depending upon input xt and past input xt minus 3. This is a present input. In such type of cases, output is dependent upon the present input and the past input, but not on the future. But in example number 2, I can see present input, past input as well as future input. We can see it more clearly if I put n is equal to 0 here. So y0 I get 2x of 0 plus 3x minus 3, which is also a past input, plus 6x3. So output at 0 is depending upon input at 3 also. That means a future value. These kind of systems are known as a non-causal systems. After this, we have the stable and unstable systems. A very important aspect here, there is a concern here like bounded input and bounded output. If input is bounded and if output is also bounded, what do we mean by the bounded? Bounded is basically if we have the finite input, with this we have the finite output, then systems are known as stable. Bounded input, bounded output, stable. Otherwise, unstable systems. So we can read it from here also, the system is said to be stable only when the output is bounded for the bounded input. A very important aspect here also, let the signal, let it be the input signal, let it be bounded with any value less than infinity. Any value, or we can say it can be any value, it can be any value less than infinity. Let it be the input. Let it be bounded for a single value, that is a finite value less than infinity. If output is also bounded for this particular case, then system is said to be stable. So we have also taken few of the examples for the bounded input and bounded output, stable and unstable behavior. Example number 1 is for the bounded and example number 2 we have taken for unbounded system.